Welcome to the e-Pathshala series in computer science. This is the 10th module in the subject of cloud computing. Today we are going to see about the time ordering of in a cloud environment. So, since cloud is a kind of distributed environment, all the systems are expected to be geographically distributed over various regions, and how these systems can be working together, cooperating or collaborating with each other using the time of the computers is the topic of today. So, in this class we will discuss the necessity of the clock, and we will see how difficult it is to not have a global clock or the absence of global clock, and we will look at methods of clock synchronization. However, first let us take a look at an example. So, here is our example. Student Reena wants to reach her class at 8:30 a.m. So, she will arrive at her class according to her watch, and if her watch is 15 minutes late than the watch of her teachers, then she will miss the class. On the other hand, if her watch is 15 minutes faster than the teacher's watch, then what will happen is she will end up waiting for a long time. So, what is required here, a solution to this is that Reena should set her clock with the teacher's clock. Let us look at another example where Ram in Chennai wants to watch the IPL final, and he logs on to the Chennai server to book tickets. He is given the message that only one ticket left, he buys the ticket. Now, the Chennai server stamps the time on the ticket saying that at 17:55 hours Ram has bought his ticket, and also since that was the last ticket sold, the message is sent to all the other servers saying that there are no more tickets left. Now, Nita in Mumbai also wants to watch the IPL final, and she logs on to a Mumbai server, and she finds that there are no tickets left. This is perfectly fine because Nita has logged on to the server after Ram, but this is the surprising fact that the Mumbai server stamps her message saying that no tickets, sorry, at a time of 17:26 hours, whereas Ram got a ticket at 17:55 hours. Now, the question is it possible, is it correct, and is it fair? So, let us look at what actually must have happened. In real time, Ram had logged in before Nita. So, therefore, Ram should have got the tickets, and he actually got the tickets. But the systems are not following a global clock. According to the global real time, Ram had logged before Nita and therefore got the tickets, but the systems are following their own clocks. So, the transactions, had there been a global clock, Ram's transaction would have shown a time before that of Nita's, but that did not happen in our example because the server of Chennai and the server of Mumbai are using their independent clocks, and these clocks do not match with each other. Just like we saw in our earlier example where we said that Reena needed to be in class on time, similarly here Ram and Nita, the clocks have to be the same. That means just like Reena had to match her clock with the teachers to be exactly at the right time in class, similarly the Chennai server and the Mumbai server in the later example we saw should have had a kind of matching of their clocks. Only then the stamping of time to be 1755 and 1726 would not have happened. So, the problem, if we look at it, we will see that there are different clocks and these clocks always will drift. So, what is a drift of a clock? The clocks never run with the same frequency, which means that even when we start 2 or 3 or 10 clocks together, eventually after some time some clocks will go faster, whereas some other clocks will go slower than the others. And the rate of change of these Q, the drift that we are talking about, are not the same. So, therefore, we cannot make an assumption that this clock is running faster or slower. It has to be checked. And then all these distributed environment like cloud depends on their communication on the internet and the thereby networked environment. And network environment, we have been seeing that is unreliable. Third point is that the machines have different processing power. So, since cloud is a very large environment, obviously we expect that different machines of different processing capabilities will be present in this environment, and therefore, they will work at different speed, their processing power will be different, and this will again cause many events in the server to have different values. So, first let us formally state the problem. What is the problem? Each machine in a distributed environment in cloud has a separate clock. The second one is the machines use their own clock for every operation. So, all local operations will be done based on the clock of the machine. Communication in a distributed environment like cloud depends on the internet and therefore, the underlying networking, and therefore, we do not have any specific time bound, and cloud is a heterogeneous environment. So, processing time cannot be predefined. So, the question that arises at this point in time is why we do not face similar troubles in our personal computers or our laptops or any desktops for that matter. In any single processor environment, the scenario is different. So, the difference is that in a single processor environment, there is only one clock, that is the clock of the machine. All processes running in that system will be using that particular clock, and therefore, they will be perfectly in synchronization with each other. But in a distributed system, the processes are running in different machines and the processors are still looking at the system clock, but here we have multiple systems or multiple machines. This is the problem that we have. So, therefore, this is identical to a real environment, real world environment, where different events happen according to the clock of the local time. So, what we are actually having a problem is that there is no global clock or global time. Every machine has its own clock, and then it is impossible to guarantee that the clocks will run together, and therefore, just like real time, we have clock drift, skewed, and hence we need to adjust with the global clock. So, finally, we arrive to this decision that we do need a global clock, and we do need all the machines to be accommodating or adjusting with that global clock, so that they are in sync with each other. So, what is a global clock? Actually, coordinated universal time, or it is called UTC, it is reversely said universal coordinated time, is a global time that is maintained with atomic clock, and the value of this clock is available even over a broadcasting station. So, therefore, anybody having a receiver is able to easily receive the value of this atomic clock or UTC and synchronize their clocks. So, how do we make use of this? So, we use UTC to synchronize our clock. So, let us look at what we mean by synchronization. Synchronization or adjusting our clock is just like what we do in real life. For all systems that are involved in a specific environment, we use the UTC to synchronize each and every clock of each and every server, hoping thereby that all the clocks will give the same time. So, there are various questions that come out of this. How often should one synchronize, and is there a specific algorithm using which we can do the synchronization? And the final question, of course, is does it actually work? So, that is what we are going to find out, whether it actually works in a real life environment. So, the first we are going to look at external synchronization. We represent a clock using a value of C of I, where I is the number of process for which the clock value we are stating. So, if each process's clock value is within a specific bound from the well known external clock. So, therefore, an external synchronization insists that we have a global clock or a server time, which is S, and every process's clock or every machine's clock should be within a certain value D with this global value of S. So, this external clock may be the UTC or it may be using the UTC time. So, how we can synchronize just in case we do not have an UTC receiver? Does it mean that a cloud system not having an UTC receiver cannot keep their server synchronized? No, we actually do not need an external clock in many cases. We can adjust the clocks of the internal environment systems. This is called internal synchronization. So, in an internal synchronization, every pair of processes that are running in the system in various machines should have their clock values within the time bound of D. So, here clock value of I minus clock value of J should be within the time bound of D, where I and J are the two processes. So, now let us look at specific algorithms to implement the synchronization process. For external synchronization, we will look at Christian's algorithm, and for internal synchronization, we will look at Berkeley algorithm. So, here is the Christian's algorithm. We have one machine which is the time server or the timer machine M1, and we have two other machines M2 and M3. Now, in step 1, M2, M3 will ask the time server what is the time. In step 2, the server will send the time server will send the time saying that here is the time T, and in step 3, the machines will set their clocks. So, this is called a timeline diagram, where every process is represented using a line, and this is how the time goes. And here is our example, where P is a process which is asking the time server S what is the time, and the time server will check its time and will send the time saying here is the time T, and this is our third step where the process P is supposed to set the clock. But is this the correct time of T where the process should set its clock? Now, let us see why this is not correct time. We have missed three very important points. One, the message sending time. We have said network delays, we have talked about internet is unreliable, packets are being dropped. So, therefore, there will be a specific a finite time that will be spent to send the message. Then this processing time, it is also some time that is being spent for the server to look at the time and send the message, and the third is the time taken to send this message. So, therefore, we have the message sending from P to S, the processing time at S, and the message sending from S to P. Here the processing time actually is quite negligible, because that is the time server and the job of time server is to do this. So, we can ignore that, but these are times that we cannot ignore, and this is called the round trip time or RTT. Now, if we look at our diagram, the RTT is the time here between T1 and T2. Now, what should we do with RTT? Actually, if we look at it, half of this time is the time that we should consider, because T was approximately calculated here. So, half of RTT is what we should adjust our clock with. So, how to calculate RTT? Very simple. We take T2 minus T1, that is our RTT, and we take this T, add half of RTT, and that should be the value of clock P. So, this is an example. This is at 10 o'clock, this P sends the message. At 10:04 it receives back the message. So, what does it do? 10:04 minus 10 by 2, which is 0.02. So, therefore, at 10:32 it sets its clock. So, now we have seen Christian's algorithm, and now we will look at an internal synchronization, which is Berkeley's algorithm. So, periodically if the time server will send its time to each client, each client will calculate the difference between its own time and the time server's time and send this value delta P to the time server. The time server will compute an average of delta and will calculate per process adjustment and will send that adjustment to every client, and the value in the clients will be the adjusted value. Let us look at an example. Here is an example for Berkeley's algorithm, where we have time server at 3 o'clock, client process at 2:50 and another client process at 3:25. In step 1, we have the time server S sending its time CS to each process. Here we see that the time server's value is 3. So, it is sending 3 o'clock to this process at 2:50 and it is sending 3 o'clock to this process at 3:25. It is also considering itself a process and sending itself the value of 3. In step 2, each process will calculate the delta P. How it is calculating the delta P? This process has got 250 and is getting the value of 3. So, 250 minus 3 is minus 10. It is sending back minus 10, saying that, hey, I am backwards or I am slower from you by 10 units of time. This process, on the other hand, is actually at 3:25, and when it gets a value of 3, it sends back saying that I am ahead of you by 25 minutes, and this server is sending itself value saying that I am in sync with your value. Obviously, it is the same server. So, now in step 3, what will the server do? The server, after receiving all the delta P's, will calculate the value of delta. In our case, the value of delta is 5. So, there plus 5. So, therefore, it will calculate that and then it will do delta minus delta P for each process. So, our value is 5 for delta, capital delta, and this process had sent a minus 10. So, 5 minus minus 10 will become plus 15. So, it will say advance your clock by plus 15 minutes or units of time. Similarly, here the value that it had sent, its delta P, was plus 25. Now, I have 5 as capital delta and plus 25 as delta P. So, 5 minus 25 will be minus 20. So, the server daemon will send a message saying that, hey, you put backwards your clock by 20 minutes, and here the delta P was 0. So, therefore, it is delta, so plus 5. So, the server itself extends its time by 5 minutes. So, it becomes 3:05. This guy will adjust its time and will become 3:05, and this guy will set back its clock by 20 minutes and will become 3:05. So, by applying the delta minus delta p at each process, we see that all the clocks now are synchronized with each other. So, this is the way we set the clock with each other. In setting the clock, there is something very important. So, when a value comes saying that put your clock forward, there is no problem. Any process is allowed to set the clock forward by whatever time it is. That should not cause any problem. But when the process, just now we saw that one of the processes in the internal Berkeley's algorithm were required to set back its clock by 20 minutes. Now, this is a big problem in setting a clock, because a golden rule in clock setting is that no clock should be set backwards. All clocks can only go forwards. A very simple example why we should not set our clock backwards is that make in Unix, make is a process where it takes a look at all the changes that have been made in a program and recompiles only those programs that have been changed in the since the last compilation. If we set back the clock by any amount of time, then when make takes a look at the whole time, everything will be in a disarray. So, therefore, a golden rule in clock setting is that we should never set the time backwards. So, if we look at this, our first example here, assume that the time was 9:50 of the server and it sends the time, hey, the time is 9:50, and we calculate the RTT by 2 and we see that the clock should be set at 9:52. So, the clock is actually at 10:04, but it should be set at 9:52. How to make this work is, we can do only one thing, we can reduce the speed of the clock. So, the clock actually is a counter which counts the number 60, and it is set in such a way that every tick happens per second. So, therefore, when 60 seconds are completed, a minute is advanced. This is how typically a clock is generated in a server. So, therefore, when we need to set the clock backwards, rather than setting the clock backwards, we just delay the count a little more, and we say that instead of 60, make it work, make it go for 70 ticks, and then create that to be a minute. So, therefore, we should never set the clock backwards. So, therefore, we are allowed to increase or decrease the speed of the clock. By increasing the speed of the clock, we can make the clock go faster than it was. By reducing the speed of the clock, we can make the clock go slower than what it was going. So, in case our clock was running ahead of time, we can slow it down by adjusting the speed. Similarly, if it is running slower, then we could set it go for faster by adjusting the speed. Now, what happens if one of the values is too large or too high or too small or is out of the range? Typically, what we do is, in fact, in all examples that we will see in future for almost all our algorithms, always there will be certain values, or there may be certain values which are not according to the range of other values or not at par with the other values. So, what we call these outside values or extreme values as outliers, and typically we disregard these values. So, therefore, in Berkeley's algorithm, if one of the clock's value is very large, in our example when we had the value of 3 o'clock of the server, if one of the participating machines would say that my value is like maybe 11 o'clock or 10 o'clock, then we should disregard or not accept that value. We should take that value out, and the average should not be calculated using that delta p. So, our delta will be calculated without that specific delta p. So, this is how we should adjust or set the clock. So, do we have all the problems resolved? So, even when we are trying to synchronize our clocks, unfortunately the drift can never be set right. The question comes is how many times we should synchronize, how often we should synchronize, and more importantly, what is the price of synchronizing. We must realize that sending the messages cause congestion in our network. The time is spent by calculating all these delta p's and deltas and drifts and how much which clock should go ahead or behind, and these are precious server time that we are spending to calculate the new values. So, synchronization actually creates big problem in a very demanding environment like cloud. In a cloud environment, every second is very precious because we work on the service level agreement with the clients, and the servers should work at full speed with maximum efficiency and should not do work other than executing the client program. A clock synchronization is besides a client program, and although it is very important to have the clock synchronized, these mechanisms of using an external or an internal synchronization may not have worked. So, further, when the drifts may be very large of one clock, we can resolve. If all the clocks are drifting very far apart, then we do not know how to solve it. And a very important question is what happens if the time server fails. This is called a single point of failure, and there have been mechanisms or algorithms which try to resolve this by generating a distributed algorithm, but some problems will arise there also. So, if some messages are dropped, if some messages have taken a longer time, and all these and many more questions arise when we come to do external or internal synchronization. So, the solution for this is what we will see in our next module. To summarize this module, we have looked at what is how the clock, the problem of global clock in our distributed environment. Then we discussed the universal coordinated time or UTC, which can be obtained using a receiver by any distributed environment like cloud. Then we looked at two algorithms. One is an external synchronization algorithm, which is the Christian's algorithm, and we discussed one internal synchronization algorithm, which is the Berkeley's algorithm, and further we discussed how to set our clock. These are our references.